Hello, everyone, and welcome to the third week in our training series. This series is a part of NASA's Indigenous People Capacity Building Initiative, and is focused on an introduction to remote sensing. My name is Cindy Schmidt, and I will be joined by my colleague, Amber McCollum. For each of the courses, we'll focus on specific tribal lands within the U.S. We will also be joined by a tribal representative who will welcome us all and speak a bit about their lands. Today, our guest will be James Rattlingleaf, who is a member of the Rosebud Sioux tribe located in South Dakota. This series will be provided via GoToWebinar each Tuesday and Thursday of October from October 6th to October 29th. All the course materials can be found on the UTTC website shown above. Please refer to this website for guidance on how to receive your continuing education credits if you are interested in that. Also, that website is where you can find all the lectures, course exercise, and the data you will need. You should have downloaded all the materials for the exercise today and follow along with our demonstration. As mentioned, this training series will be a mix of lectures and hands-on exercises. All the exercises will be conducted in ArcGIS Pro and will be demonstrated in class. But we do have some materials for ArcGIS Desktop and QGIS, but they will not be the focus of the series. And we will focus on a different tribal region each week. So here's a general overview of the training series. This week, week 3, we're focusing on change detection today, and then time series on Thursday. And then next week, our last week, we'll be demonstrating some remote sensing web tools. So the objectives of today's lesson is first to define change detection for remote sensing. So what is change detection? Identify the best images for use in change detection, describe different change detection methodologies, and lastly, of course, to conduct the change detection exercise. But before I get into the lecture, I'm very proud to introduce my friend and colleague, James Rattlingleaf from the Rosebud Sioux tribe. Over to you, James.
Daya Yahapi. Welcome all to the Remote Sensing for Tribal Lands training course. My name is James Rattlingleaf Sr. And how we greet ourselves in Lakota language is, I would say, How Midakiapi Chante Washted Napechi Zapalo, James Rattlingleaf Sr. Again, my name is James Rattlingleaf Sr. I'm from the Rosebud Sioux tribe, and I was given the privilege and honor to give a little opening remarks on some of the work that I've been a part of for these past years, and also my association with NASA. And so I have a role today to speak on remote sensing from a tribal perspective. And so the images you see on the bottom here are affiliations that I'm a part of. So I work in climate, I also work in earth observations, work with tribal cultural heritage, and also work with my tribe, the Rosebud Sioux tribe, on climate change planning. So my association with NASA goes way back. Look at that young guy right there. Still doesn't know very much, but it began in the early 2000s. And so with this article here, I was called an Earth Explorer, and they wrote an article on the work we did at Rosebud. And so I'm going to talk about our work at Rosebud and really show you kind of how we approached remote sensing and these technologies. So NASA. So I have an affiliation with NASA, and it's been a very good association, and I continue to work with NASA and other ways. So Rosebud, we looked at approaching this technology back in early 1998. So these images are really pictures of the work that we've done through direct partnerships with the federal government. We worked with our elders to help us define how to best approach the technology. And then we also looked at how we might support these projects. So we really thought hard about funding. We thought hard about the political support. Really thought hard about education. How do we prepare our students at the tribal colleges to use this technology, the data and the science? And also, we are also inspired by our leader, Itancha and Lionel Bordeaux, who really challenged us to think about this technology, remote sensing, both from a physical part, but also a spiritual part. So out of that work, it was important that we define how we wanted to articulate what remote sensing or GIS was at the time. So we had one of our elders, Mr. Albert Whitehat, the late Albert Whitehat, and so we presented some images to Albert, and we asked him to interpret that in a Lakota language. And so he said, James, what you're talking about is this. He said, James, this is how we would say it, or how we would define GIS. It's Unchi Maka Naha Wichakpi Oyate Naha Omakashka Oyate Wo Lakota Glusutapi. So he's talking about Mother Earth. He's talking about Star Nation and all things that live in those areas working together in harmony. And so ResMapper was a product of that, where we brought technology, software, data together to really show the people of Rosebud about this technology, and to show the local community, both from a mapping perspective, a data perspective, also bringing in photographs of historical leaders like this one here you see, that's Two Strike, and bringing other data into it so that people can kind of see, and people can begin to think about how the state data could be used for their work as well. We also wanted to talk about sort of the cultural underpinnings of why this is important. So this is a remote sensing image of the Black Hills. And also to the right of that is an Amos Badhartbull rendition of the Black Hills. So even our ancestors knew what the Black Hills looked like, even though they didn't have remote sensing. They just had another way of knowing that. And so these are names of important places in the Black Hills that are important to our people yet. And we still advocate, we still work with, and we still have this responsibility to protect those places. Again, here's another image of it. I think this is important, understanding that not only can you use remote sensing for traditional government services, but also you can look at cultural applications like this one. Again, this is the Black Hills, and again, this is also another poster of students who worked with us on a summer camp. And so they went into the Black Hills and helped map some of these places here and named them. So this is important for us to demarcate these places in our own languages and continue to promote the Lakota language. So Rosebud, through this development, through this time, began to build a capacity to develop GIS programs. So I like this one here, Rosebud Sioux Tribe, Wajiji Tchta Waji, One Rosebud Project. Again, really trying to understand our needs for data and for information. Wind resources, renewable energy is another important part of this work. How do we use remote sensing to understand the resource, so to speak, but also planning for it? We also did a language project here with remote sensing. So we're teaching the Lakota language. This map here is, again, it's soils. It's bringing different information together. We also looked at fire applications on Rosebud. That was a fire that we had many years ago, but again, remote sensing can show us the extent of that. And then finally, I wanted to honor one of our local leaders. This is Dr. Victor DeVille. And Victor's work around this technology has been very inspirational to me, as I was part of this work and led this work and followed this work. And he and others like him are important in terms of your strategy so that you can get support for this work. So the work continues. And so there's a picture of Cindy and Amber Jean here, and myself. I had a chance to help facilitate a meeting, a remote sensing training meeting last year in Bismarck, North Dakota. Also, there's a movement to bring Indigenous people together around remote sensing technology and data. So there's a new group called the Geo-Indigenous Alliance. So we're coming together as Indigenous people and trying to use Earth observation or remote sensing to help protect our cultural heritage. Youth is an important part of this initiative. So we have this thing called a hackathon. And so youth are involved with mentors to help solve problems with remote sensing using application technology. And these two images here are really important. This image of a satellite dish is from Australia, and there's a Lakota star map on that. Isn't that interesting? And then also this book. I brought this book in. It's Tribal GIS. Again, this is a book that really talks about how tribes around the country in America are using GIS for planning, for protection, for environmental services, for education and such. So there's a lot of work that's been going on, and I think the work that you're doing here through the training obviously is going to complement that. And so you're in great company as you pursue this work with remote sensing. And I think that, you know, as we think about this training and why that we've been doing what we've been doing on Rosebud, I think that we have these four things that are important. Remind us again, you know, there is a need to restore the balance to care and responsibility for people and the earth. I think despite this new technology and our wealth, we still have these real serious problems. So we got to continue to work on that. I think as tribal people, I think we've done our best to raise the consciousness of these issues with the world, with our country here. So we continue to do that. I think that's our responsibility. And finally, I would say is that we need all ways of knowing. In my 25 plus years of working in science, never have I ever where we have science organizations really talking about understanding and working more respectively with traditional knowledge or our knowledge. And so those things are happening now. And we hope that these things will continue in a respectful way. And finally, I want to leave you with this last slide. You notice the slide, this is 3 men on a horse, and they're looking for the next campsite. And you notice that they have sort of new tools. They have a gun. They also have the horse, which came to us, you know, in the 1600s. It was new to us, but yet somehow we chose to embrace new things. But we also brought it into our culture in a respectful way. And so we made it a relative. And now that we have that, now that we have our ancestors' sort of pathway of how we bring in new things like remote sensing, like technology and science, we also have to understand too that satellites and those sort of tools also can be part of our future, can be part of our decision making in terms of preparing our tribe, our people, our students for the next generation, so that we can be good stewards of the earth. So I want to leave you with that we do have in our DNA, in our history of embracing new technologies, but we do it in our way. And I think that's the point I want to make, is our ancestors sort of put forward these things, these processes, so we can do it. So I want to thank you for listening with me today, and I just want to conclude with my contact information. You know, we're continually working to support tribes, tribal resource managers, and these organizations I work for. We continue to help and support you as folks who are working with this technology, and certainly we thank NASA, Cindy and Amber, for their work working with you and building your capacity to use these tools more effectively. So thank you for listening to me. Wopi Latanka, Ichi Chapalo. Thank you very much.
Okay, thank you, James, for that really great talk that you just gave. I always love to hear you give presentations. So now we'll go ahead and get started with our lecture for change detection. So change in satellite imagery generally refers to the conversion of the landscape from one feature type to another. Examples of that include changes in tree cover due to wildfire or land clearing, urbanization, and land degradation due to overgrazing. The type of information you can get from satellite imagery is where and when has change taken place, how much and what kind of change has occurred, and what are the cycles and trends in the change. So what are reasons we would want to do change detection with satellite imagery? They're used for a lot of different, this methodology is used for a lot of different applications, things like natural resource monitoring, looking at deforestation, forest regeneration, urbanization, and so forth. To explain environmental phenomena like glacial retreat due to warming, to assess damage due to various disasters like floods, burnt areas, drought extent, etc. And finally, to develop or validate explanatory models. So for example, to test an urban growth model. There's lots of different types of change we can detect with remote sensing, including seasonal change. So this is a great example. As you can imagine, if you had an image of this area at different seasons, you're going to see things very differently with leaf on or leaf off, or different stages of leaf on or leaf off. We can look at things like urban development. So this is an example of how Dubai has changed from 1991 to 2017, and obviously that would be a very striking change using satellite imagery. And probably the most common way of using change detection is for different kinds of vegetation change. So in this case, this is an example of an area that's been logged or clear cut and then is regenerating. And so you could detect all of that over time, and you can look at 2 points in time, or you can look at many points in time. So we'll talk about that in a few minutes. So there's several broad categories of change that you can detect with satellite imagery. Those include the change in shape or size of patches. So urbanization is a great example of that. Slow changes in cover type are more difficult to detect than abrupt changes due to wildfire or deforestation. Slow changes in the condition of a single cover type, like forest degradation due to insect or disease, can be easy or difficult depending on the extent of the damage. Lastly, changes in the timing and extent of seasonal processes, such as decreased rainfall and its effects on vegetation, can be monitored using satellite imagery. The way we detect change using satellite imagery is by detecting changes in spectral values of pixels. And that's the key to this whole thing. Pixels will have different values before and after changes have occurred. In this example, we see that healthy vegetation has high reflectance in the near infrared bands, but low in the shortwave infrared bands. Burned areas are the opposite, with low reflectance in the near infrared and higher in the shortwave infrared. So you can use that information to not only detect burned areas, but also detect the severity of burns. The goals of detecting change in satellite imagery include identifying the location and type of change, quantifying the change, and assessing the accuracy of the results. It's important to understand that identifying the location of and quantifying change is pretty easy. Identifying what caused the change is the challenge. So what kind of data, what kind of information do you need for change detection? So obviously, change detection requires multi-temporal data sets, right? So you need more than one image in time in order to look at that change over time. And when you select these multi-temporal remote sensing data, it's important to use, if possible, the same sensor, the same spatial resolution, and ideally with anniversary or very near anniversary acquisition dates. And the reason why you need to do all of this stuff is because you need to minimize changes due to things you're not interested in, so that you can identify the changes that you are interested in. So the key to successfully detecting change is to separate real change from spectral differences that are due to other factors, such as images from different seasons, if you're not interested in those different seasons. So you need to choose images that are collected at approximately the same time of day, collected during the same season, as cloud-free as possible, co-registered with one another, and radiometrically and atmospherically corrected. And the reason you need to get all imagery with those characteristics is because You need to reduce differences in sun angle. You need to minimize differences, phenological differences. And the other thing is that you need to think about sort of the atmospheric condition between those two different dates, because the atmosphere will not be the same in each date, no matter how close you get to the anniversary date. So the further apart you are from those anniversary dates, the more different the atmospheric conditions will be, which may affect your pixel values. Also, going back to sort of different precipitation amounts, that's another thing to be aware of. Even though you're looking at anniversary dates, if you have different precipitation amounts each year, as you can see in this image, that's also going to affect your spectral characteristics of that image, unless you're interested in looking at differences in precipitation amounts. So the accuracy of change detection can be affected by a lot of different factors related to what I just basically described to you. So it's really important to have precise geometric registration between multi-temporal images. So those images need to align exactly the same with each other, because if they don't, then what you'll get is change due to this misregistration of images. These days, that tends to not be as much as a problem as sort of back in the day when there would be some issues with registration, but it's a good idea to check anyways. So the calibration or normalization between multi-temporal images can also affect your accuracy of the change detection. And then obviously availability or quality of ground data for training or validation. And lastly, actually not lastly, second to lastly, the complexity of landscape environments of the study area can also affect your change detection. And as you've seen by doing the classifications, it can actually affect just about everything that you do in remote sensing. So it's something you have to sort of keep in mind. And then of course, the methods or the algorithms that you use will also affect the accuracy. The classification and change detection schemes make a difference, again, as we saw in the classification exercise. And of course, the analyst skill and experience, which hopefully we're helping with that, with our courses that we're teaching you. Lastly, not lastly yet, knowledge and familiarity of the study area, of course, is important. And this is lastly, time and cost restrictions. So next I'm going to talk about a few methods used for doing change detection using satellite imagery. So there's a couple different types of change detections when you're working with satellite imagery. One set of change detection types are between class changes. So the type of question that you might ask with between class changes is, has a pixel changed between different classes, and what has it changed to? So a great example is forest to agriculture conversion, or agricultural to urban conversion, or something like that. Within class changes is a little more, those are a little more subtle changes. So they're based on, continuous spectral or transformed spectral information, and answers the question, how much and in what direction has a pixel changed? So has there been a change, for example, in percent vegetation cover? So as you can tell, that again, that's a much more subtle change, and also can be a little bit more challenging. So there's a lot of different ways to check change detection, to check change in imagery. So we'll be talking about 4 in this course. visual analysis, classification approaches, image differencing, and lastly, temporal trajectories. So visual interpretation really involves, it's pretty basic. It involves the delineation of change on a computer screen, so something that we typically call heads-up digitizing. So rather than doing it on a paper map, you just do it on the computer screen. And so, the benefits are that it allows production of results that are automatically in digital form. And it's good for looking at very large changes, like shape or size of large patches. It's not quite as good at looking for subtle changes, like land degradation. And I guess the biggest thing about this approach is that it really doesn't take advantage of the entire spectral variability and spectral response using satellite imagery. And this is just an example of a visual comparison of a lake in Northern California that experienced quite a bit of decline in water quantity from 2014 to 2015. So that's an obvious change that you could probably delineate using heads-up digitizing. So another classification approach is called post-classification comparison. So that's essentially where you take two dates, or you could take more than two dates, but it gets more complicated the more dates that you use, and you actually classify them separately. So you go through the same, whatever supervised classification process, whatever classification process you prefer, you do that separately for each date. And then essentially you just subtract one image from the other to identify what that change is. This is really kind of a rough way to do change detection because as you have all found out by doing a supervised classification, there are errors associated with a classified map, right? And those errors will be kind of multiplied when you use two maps and try to subtract them from each other. It also does, because it doesn't really take full power of looking at the change in spectral response, it tends to ignore more subtle changes within a class. So we don't like to advise doing this approach for those reasons. So this just gives an example of how that works. You essentially do the classification of one date, and then you do a classification of the second date and put them together, and then you do the subtraction to get the changes in the land cover types. So another approach, and this one is I would say more preferred than the one I just described, is actually stacking two dates of imagery into one file. So you take two different dates, you put them all together in one file, and you actually classify that. And that actually works much better because your change classes will be unique, will have unique spectral characteristics. As you can imagine, it's kind of it's a great approach for looking at subtle change. It can get challenging to try to interpret where the change classes are, though. So this is just a graphic of what that looks like. So you take the date 1 imagery and the date 2 imagery, you put them all together in a combined image, and then you run like a supervised classification on that. And then this is just a picture of an example of that. So it's a land cover change from 1999 to 2009, and it's a little hard to read, but the legend basically says what the original class was and what it changed to. So these are just change classes that we're looking at. The other very common way of looking at change over time, especially if you're just looking at a couple different dates, is to take a single band of image and subtract one date from another date. So the resulting change image consists of positive and negative values where change has occurred, and zero values where no change has occurred, in and around zero. The advantage to this approach is that it can detect very subtle changes, but again, it may be challenging to interpret. And this is just a graphic of what that looks like. So you take image date 1, you subtract it from image date 2, and then you get these change values where 0 means no change, and then the values in any other direction mean, whether it's a positive or a negative, mean change. And so you have to interpret what that change actually is. So calculating the difference normalized burn ratio, the NBR, is a really good example of image differencing between the image transformations of two dates. So as I said before, if you do image differencing, you can do it on a single band, but you can also do it on image transformation. So you can use NDVI or other kinds of ratios. And so the normalized burn ratio is another example of transformation. So this approach involves calculating the normalized burn ratio for each image and then subtracting the post-fire normalized burn ratio image from the pre-fire normalized burn ratio image. So this gives you that change image, and in this case, it shows you the severity of where the fire occurred, of course, and then the severity of that fire. Recent developments in change detection methods take advantage of the entire freely available Landsat archive by using monthly or annual time series to look at changes or trends. While in the previously described method, you would only use maybe 2, maybe 3 image dates. In this method, you can use 20 or 30 or more image dates. So this method allows the capture of short duration disturbance events as well as long-term disturbance trends. So this is something that we'll be talking about more in the next session on Thursday. And we'll be showing you some more examples of this. But this is really, I think, a great methodology to use, especially when you're interested in very subtle changes and you're interested in changes that occur either in very frequent time intervals. So the approach is actually founded on the recognition that change is not simply, so you're not just comparing between 2 points in time, but you're looking at change as a continual process, operating at could be at fast and slow rates on the landscape. And so this particular example is of an algorithm that was developed at Oregon State by Robert Kennedy, called LandTrender. There's other ones out there as well. So the results of this algorithm include the magnitude of change that identifies the percent of tree cover loss, the duration of disturbance, and the year of onset of disturbance. So a lot of these temporal trajectories were really developed to focus on forest change because that's fairly easy to detect over time. Some of the other landscape changes are a little more subtle and a little more challenging. So again, we'll talk about that a little bit more in the next session. So I just wanted to show you some case study examples of change detection. So this example shows you how you can clearly see some types of extreme changes like mountaintop mining in West Virginia. These images show the elimination of vegetation for mining operations between 1984 and 2015. So the resulting rock debris piles have increased sedimentation in nearby rivers. Fan et al. Used a vegetation index differencing approach to map rubber plantations. So this is a little different than analyzing change between two time periods. It identifies rubber plantations by taking advantage of the two distinct phenological stages, leaf off and full foliation. These two distinct phenological stages enable identification of rubber plantations compared to the surrounding vegetation. So this is a very common way of identifying certain land cover types by looking at two different time periods. So this approach could then be used to look at the expansion of rubber plantations over time. This example shows the changing land use and land cover in a watershed in Southwest China between 1974 and 2008. This study used the post-classification comparison approach, which will not capture subtle change, but as you can see, it does capture broad land cover changes. It's also easy to quantify the changes with this approach. So lastly, I'm just going to talk to you a little bit about what you're going to be doing in exercise 6 today with the change detection exercise. You're going to be doing a couple different methods for looking at change. The first one will be a visualization method. So it won't be the heads-up digitizing that I actually described before. One of the things you can do is you can put different dates in different color bands in the software, and you can automatically highlight where the changes are. So that kind of shows in this picture right here, where we're looking at some floods in South Dakota. In 2018, there weren't any floods, and then in 2019, they had huge floods in the spring. And then on the right-hand side, you can put different bands in different band combinations for the different years to have the flood areas just pop out right at you. So it's a good way of looking at where the change is, although with this methodology, you can't quantify the change. The other methodology that you're going to do in the exercise today is the image transform approach that I described, and then do the subtraction between the two different dates. And this way, you can really visualize and quantify the change a little bit better than just the visualization approach. But you can really only identify the cause of the change using sort of expert knowledge of the region, although flooding is pretty obvious. So the approach is to conduct a normalized difference wetness index on each image, and then you're going to subtract one image from the other. So that's it for the lecture today. We're going to Amber is going to take you through the exercise next. And I just want to remind you that on Thursday, our next session will be on time series. So Amber, over to you.
Great, thank you, Cindy, for that really clear overview of the different methods for change detection. And as Cindy mentioned, we're going to be analyzing a few different methods for assessing change during the flooding that occurred in much of the Midwest in the spring of 2019. And we'll be focusing on portions of the Missouri and Mississippi rivers, primarily in South Dakota. We're sort of on the border of South Dakota and Nebraska as well. Which is a little bit east of the Yankton Reservation as well as the Rosebud Reservation. So if you all are following along, this is exercise 7 for change detection. I've just started up my ArcGIS Pro here, And the first thing that we will be doing is just starting a new map. And we are going to call this exercise 7. And I am going to navigate to my desktop where I have a folder for this demonstration in particular. So navigating to my NASA IP demo folder here. You will be navigating to your exercise 7 folder, just a little different there. Click OK, and we'll be just starting a new project. So we will be analyzing Landsat data from 2 different dates. The first date is the pre-flooding image from May 7th of 2018. Then we will be analyzing a post-flooding image, which actually was sort of during the floods from April 8th of 2019. So as Cindy mentioned, we try to obtain images around the similar time frame each year, so that we are only analyzing change that we want to analyze. So those were the 2 closest dates that we could get a year apart that weren't fully covered by clouds or had a lot of reflectance issues relative to clouds covering the area. So the first thing we will do here is view our catalog pane to add our Landsat image bands to the map and create our composite image. So if we look at the catalog pane here, we can just use this little arrow to down click next to our folder, and we should be taken to the folder in which we save this project to, which also should have our Landsat images here. So you should see your Landsat folder here. And we are going to start with the 2019 image. So this is the 2019-0408. So we just click next to that down arrow here, and we are going to add the bands 1 through 7. We can use the Shift option to select all of them and right click and then add to current map. So now we can see our Landsat image and where it is located here, sort of in between Sioux Falls and Sioux City. I'm going to go ahead and turn off my world hill shade for now to allow this processing to not be slowed down by that, but you're always going to have your topographic and hill shade map as the default, which you can turn on and off to orient yourself in space. Great. So the first step we're going to do is the analysis tools, and we are going to search for composite bands. And it's a data management tool here, and you can just double click on this and we can run this process. We can close our catalog pane for now and take a look here. And our input rasters are just going to be those 7 bands of our 2019 Landsat image. And we want to make sure that we add them in bands 1 through 7 in order, so that when we create the composite image, all of the bands are in the correct order, 1 through 7. So these are the input bands here. And then we're going to navigate to our folder, and we are going to save this image as our Landsat 2019.tiff. And make sure you're using the TIFF extension here. And then we're going to click on Save and Run. Okay, so now we can see that the process has completed. Our new Landsat image is loaded here in our contents panel. We will change the color scheme in a moment. First, we are going to remove some of these additional bands that we added in, and then we're going to complete the composite band step again for our 2018 image, and then we'll start to compare them. We will be using bands 5 and 6 later on in some of our analysis. So let's go ahead and remove all the bands except for those two. And you could just do this by right-clicking and clicking on Remove for each of these here. You can also select multiple bands and remove them all at once. So now we should have our Landsat 2019 as well as the bands 5 and 6 from the 2019 image. We are going to go ahead and rerun this process for our 2018 image. So let's go ahead and close our composite bands for now. We are going to open up our catalog pane again, and now we're going to add the 2018 bands. We're just repeating that same step for the 2018 image, the pre-flood image. So here again, we're going to select bands 1 through 7, right-click and add to current map. Then we can close the catalog pane and do our analysis tools and composite band here. And that was a recent tool we used, so it should show up here, and we just can double click on it there. Now again, we are going to add bands 1 through 7 of our 2018 image. And we're going to go ahead and save this one as Landsat 2018 TIFF in our same exercise 7 folder here. And again, click Run. And the same process will run, and we should receive a composite image that contains 7 layers for each of those 7 bands in our new image. All right, so now we have our 2018 composite image here located on our map. We can close our geoprocessing tool here. And again, we will remove each of the bands except for bands 5 and 6, which we will use later. Great. So now we should have our 2 composite images. We can just move the 2019 image here. So we have our 2018 image, and we can turn these on and off and start to look at differences. But before we visually interpret these images, let's change the band combinations to something that is a little more clear and makes a little more sense. So what we're going to do here is right-click on our Landsat 2018 image, click on Symbology, and we are actually going to change these color combinations to a 7-6-4 combo. So 7 and 6 are the shortwave infrared bands. We'll be using those quite a bit. And then our 4 is going to be our red band. So 7, 6, 4. And now we can start to see healthy green vegetation as sort of this darker green color. And the yellows are representative of maybe sparser vegetation or vegetation that's just starting to grow. We are early in the year for this region as well. So here we, again, we see the vegetation as green, and we can start to pick out these river areas as well along the map in the 2018 image. So let's just close the symbology here, and we'll do the same band combination for 2019 because we want to be able to compare the images in a similar manner across both of these dates so that we can really pull apart the change that we're observing. So now what we can do is we can turn on and off our 2018 and 2019 image, and straight away we can start to see some differences here. The benefit here of the use of the 7-6-4 is that we're using the shortwave infrared bands as well as the red bands. So the vegetation will be displayed as green here. So let's go ahead and just take a look at the image. I invite you all to zoom into different areas, take a look at the rivers. So you can see here is the 2018 image, for example. You can see this meandering river along here. And if we just turn off our 2018 image and we're looking at the 2019 image, it's very clear that we can see some flooding already occurring in this region along the riverbanks. So these dark blue areas are the areas of the fields that were flooded due to this rain event. So that's one way you can start to visualize by just kind of clicking on and off and taking a look at your map with these two different images here. So the next thing we're going to do is examine the shortwave infrared band for each of these dates. And this is important because water absorbs very highly in the shortwave infrared. So when there is more water, we will see less reflectance in band 6. And this is a really clear representation of the difference between areas that have received more water or have freestanding water versus areas that are dominantly vegetation or bare soil, for example. So you can really pull apart these differences. And this is one way to start to visualize these changes. So what we're going to do here is we're essentially going to create a new composite image of the band 6 from 2018 and 2019. So I will just come here and zoom to layer. So we're looking at the entire image as we had before. We are going to use the composite band tool again, which should be here. And now our input rasters are going to be the 2019 and 2018 band 6. So the first input raster will be our 2019 band 6. And the second will be our 2018 band 6. And now we are going to go ahead and save this new composite as SWIR, shortwave infrared, 2019 because that's first, and then 2018 because that's second, .tiff. And again, we're going to save this to our exercise 7 folder here and click run. This should run a little faster because it's just creating a 2-band composite. And now we can see this new composite image shown here. What we are going to do here is modify the which bands are displayed as red, green, blue so that we can really highlight these changes. So let's go ahead and right click on our new image and go to symbology again. And what we're going to do here is we're going to put the 2018 SWIR band, band 6, in the red. We're going to put the 2019 SWIR bands in the blue and the green. Now, what this shows us is that the red areas are going to indicate regions where there is higher reflectance in the shortwave infrared from the 2018 image than in the 2019 image. And as we mentioned, the water absorbs this wavelength range really highly. So these are areas where there is more reflectance or less water in 2018 and less reflectance or more water in 2019. So again, really highlighting the flooded regions along the rivers. So here we can go ahead and close this symbology and again, take a look at these major rivers in our map. So we took a look at this area here before. Maybe we could come up closer to Sioux Falls. And the red regions here are going to indicate regions where there was more water in 2019 and less water in 2018. So that's one way to, another way to start to visualize some of that change. As always, it's a great idea to save your map along the way. You can just use this saving project tool here. A nice thing to do, especially as we move from different parts of the exercise. So that concludes the first part of the exercise. Now what we're going to do is look at transformations in part 2. So as we've done with other exercises, we looked at, for example, the NDVI, which is an index of vegetation health. We are going to use a different index here called the Normalized Difference Water Index, or NDWI, that really highlights the near infrared band and the SWIR bands. So those are going to be, in this example, the bands 5 and 6. And you can see the equation for the NDWI in your exercise. And we'll actually be running this calculation through the raster calculator. So very similar to the way we did this for looking at NDVI. So we're going to calculate the NDWI for these two different dates, and then we're going to create a difference map so we can really identify the differences in water from these 2 years. So what we're going to do here now is we can just come in, again, I like to just zoom to layers, so we're looking at the entire layer here. We are going to go again to tools, and this time we are going to look for raster calculator. This may be familiar to all. You worked on the previous exercise. And this is going to be an image analyst tool here in our raster calculator. And we have this familiar interface here that we've had before. And what we're going to do here is essentially create this equation where we have band 5 minus band 6 divided by band 5 plus band 6. So we're really highlighting the differences in between the reflectance or absorption of really SWIR, the shortwave infrared here in this example. We'll start with the 2018 image. So just follow along again, be very careful with the steps here. The first thing we're going to do is use our float operator. So you can scroll down here and double click on float. This is really important so that we can have values that have decimal points in the newly created image, which are NDWI, as with all other indices, should fall within -1 to 1. You'll see something a little different here, but we can talk about why we see that. So we want to be able to have those decimal points. So always use float. And then the next thing we're going to do is click on the 2018 band 5, or the near infrared band. So here 6.5, so we'll double click on this. Then make sure we come back within the parenthesis and use the operator to click on minus. And then we're going to subtract out the 2018 band 6. So we have band 5 minus band 6 divided by, again, float. And this time it's going to be band 5. Come back inside your parenthesis, plus band 6. Now it's always a good idea to double check this, make sure it looks right. Make sure you're using both the 2018 bands. And then for our output raster, we are going to call this one NDWI 2018. And it looks like I needed to double check this because what I forgot to do was put in my division sign here. So anytime you have your map algebra expression and there's a little X there, that means that the equation's not quite right, which is a really nice thing to double check before you actually run the process. So what we should have here is float our 2018 Landsat Band 5 minus 2018 Band 6 divided by float our Landsat 2018 Band 5 plus 2018 Band 6. So just double check that, call your output raster NDWI 2018 TIFF and click run. And maybe cross your fingers that you did it all correctly. And that happened pretty quickly. Our new raster was added to our map here. You can see that there are values that actually fall outside of our 1 to -1. And this is oftentimes likely due to pre-processing of the images before you receive them. You'll notice in these images that there are some clouds in portions of the image. They're very small. They're not really affecting the regions we want to see, but that sometimes can have can create issues when running your indice calculations like this here, where there was maybe some over-processing done in the image due to clouds or some other quality check within the data. Don't worry about it now. We'll change the range that we're interested in viewing later on, but just as a heads up that can happen sometimes, especially if you're looking at a large area and you have influences from overprocessing or the edges of the imagery, things like that. So oftentimes we try to do our best to clip these things out of the image or create a cloud mask, but sometimes that lingers in our calculation. Not a problem. So what we're going to do now is we're going to run the same process for our 2019 image. I'm just going to go ahead and close this and reopen it just to make sure we're starting from scratch. We're going to use our raster calculator again and create the same equation for our 2019 image. So again, we're going to come here and use float. And our 2019 Band 5 minus Band 6. I'm going to come inside the parentheses. Band 6 divided by, which is what I forgot last time, float again. And this time it's Band 5 plus Band 6. So it's just a simple ratio here. Okay, looks like according to our raster calculator, it's an expression that is valid. Let's go ahead and just take one look here and make sure that we're using the correct bands. 5, 6, 5, 6, 2019 minus plus looks pretty good. Now we're going to save this as NDWI 2019 and run this process. Okay, now your 2019 NDWI image has appeared here, and it may look a little funky. As you can see, it looks very white. So again, as I mentioned, there are probably some values that are throwing off the way the image is being displayed here. It's not necessarily an issue with our calculation that we've done. So don't worry, you should get the same thing like this that you see here, and we'll address that. So go ahead and close your geoprocessing tool. And the first thing we'll do is just take a look at the symbology for our 2019 image. So we can right click on this here. And if we identify the stretch type as standard deviation, this looks better. This looks more similar to our 2018 image, even though the values are a little outside of our range that we're interested in. Now it looks similar to the other image and doesn't look like a problem here. The stretch type could really help, and this essentially is not doing anything to your values. It's not making any changes to your data itself. It's just changing the way in which we are visualizing or displaying the data. So with the standard deviation, we're essentially cutting off the values outside of 2 standard deviations that may be influencing the way the image is being visualized in the software. So you can oftentimes play around with the stretch and look at the histogram of your data to see how to best display and visualize your data. Again, this is not going to affect the values, so not to worry there. Great, so the next step that we're going to do is we're going to add some symbology and classify the image in a specific data range that makes sense to us when we're looking at indices of, for example, here, a water index, where we want to evaluate values between 1 and -1. So what we will first do here is we will close the symbology for 2019. We will open up the symbology for 2018. And what we're going to do is essentially choose our symbology and assign it to classify. So we want groups of values. Now, what you will see here, I'll actually turn off my 2019 image so you can see this in real time. What you'll see here is that the default is 5 classes with these natural breaks. So it's essentially evaluating the histogram of the data and creating breaks that seem like they make sense based on what the data are, and just applying this color scheme here. We're going to modify this a little bit to make a little more sense to us. The first thing that you need to do is change the number of classes. And you need to change this while you have natural breaks selected, because once you change it to the method that we're interested in, you won't be able to change the number of classes. So do this and change the classes to 11 first. And then we want to do this manually. So the method will come here and we'll look at manual intervals. So you could see here that it grays out the classes for some reason after we've selected manual. So we need to have that 11 selected first. The color scheme we're going to use is called precipitation. What I like to do oftentimes is have show names selected, and then you can see the color scheme, but you can also see the name, so you can make sure you find the right one. There's so many different color schemes here that you have the option to modify. And this is just one that I selected based on what I thought made the most sense to me conceptually. You might feel a little differently, so you can always modify the color scheme here. But if you'd like to follow along with us, we're using the precipitation color scheme. And now what we're going to do, since we've selected manual interval, we can kind of make this a little bit bigger so we can see these different class values. And we're going to modify this to only color up the values between 1 and -1. We'll actually start here with -1. So what you can do here is double click on the value and just type in your own value. And we'll do this as I've indicated in the exercise we'll start with -1, and we'll just do intervals of 0.2, so then we'll do -8. It's a little tedious, but that's okay. We'll only have to do this once, and then we'll do -0.6, -0.4, -0.2, and then 0. And then 0.2, and now we're just doing the positive categories of the same designation. 0.4, 0.6, 0.8, and 1. Okay, so now you can see here along your context panel that we are only visualizing values between -1 and 1, where values closer to 1 indicate water. So values close to 0 won't indicate much in terms of the water values, but again, we're looking at the 2018 image here. So what we can also do to save us time in the future is if we want to save this symbology, because we want to apply the same symbology to the 2019 image so we can easily compare the two, what we can do is save this, this symbology file. So what we're going to do is right-click on the NDWI 2018 here and click on Sharing and Save as Layer File. And what we're going to save this as is NDWI 2018.tiff.lyrx. And this essentially just saves that color scheme that you have. So now what we can do is we can close the symbology for 2018 and we can apply the same thing to our 2019 image. Just turn that one on here, click on symbology. And if we come here to the these top 3 lines, we can import. And we should be able to find the file that we just created within our exercise 7 folder. And click OK. And now we can see very nicely that that same color scheme has been applied to our 2019 image. So what you can see here now are the NDWI values, so measure of water content from our 2019 image to our 2018 image. You can also turn off some of these bottom layers. You can remove these single band images if you'd like as well, but my computer may be running a little slower than yours. So you can turn these off and just take a look at the NDWI images. You can also turn these off in particular to orient yourself. So I mentioned we were sort of in between Sioux Falls and Sioux City here close to Yankton. We have the Missouri River coming down here, and we can turn these on and off. And right away in the 2019 image, you can see, again, along these rivers, we are seeing a lot of high moisture content outside of where the river channels are usually occurring. So these regions here where we see these blues, these values closer to 1, the NDWI is indicating high water content in these regions of these flooded fields. So you can come in and take a look at specific areas, turn the layers on and off, and just sort of visualize the differences between the 2019 and 2018 NDWI values. You can see along this riverbed here, there's not much moisture with the river being identified in the 2018 NDWI, but when we turn the 2019 on, we could see the river and flooding over the banks of the river here. Great. So that concludes part 2 of the exercise. The final step that we're going to do is essentially do a, now that we have conducted this single date transformation, we are going to show the difference in the NDWI value from 2018 to 2019 to really identify to quantify really how much flooding we're seeing in 2019 compared. So what is the difference between these two values? And that's fairly straightforward since we've already created these NDWI maps of each of the dates. So again, I'm just going to zoom to layer. And for this, we're going to use raster calculator again. So come to your analysis and your tools. You should see raster calculator as a recent tool here. And similar to what Cindy showed in the lecture where we were looking at the normalized difference burn ratio, this will essentially be the normalized difference water index or water ratio. So what we're going to do here is just subtract the 2018 NDWI from the 2019 NDWI. So what we should see then is in the differenced image, values closer to 1 indicate areas that were had higher water content or flooded regions in 2019. So here again, we're going to use our float operator. And we are essentially just going to take the NDWI 2019 TIFF and then subtract inside the parentheses. Make sure you're inside the parentheses. The 2018 NDWI. Great, so now we're going to navigate to our folder and we are just going to call this NDWI diff.tiff, diff.tiff. And so this is the differenced, this will be the differenced image, and this will really highlight those regions that were flooded in 2019. Everything looks okay, double check, and we will click run. All right, so that worked pretty well for us. We'll close our raster calculator. We are going to color this up a little differently because what we're looking at is the differenced image. So areas that are going to show as closer to -1 will be less water, and areas closer to +1 will be more water from 2019. So we're just actually going to start off with that symbology that we created from our NDWI and then modify it slightly. That'll save us a little time. So we can come here to our differenced image and go to symbology. And again, just import the symbology from 2018 like we did before. Which looks pretty good. But as Cindy talked about in the lecture, the values close to 0 are going to indicate no change or relatively little change. So if we want to really highlight the flooded regions, another way we can visualize this is by changing those colors to gray. And then we'll only really see the much drier or much wetter areas from 2019. So I'm going to just come in here and change our -0.2, our 0, and our 0.2 all to 20% gray. And you can do this by just clicking on this little color icon here, and 20% gray is the second one. You can use the third one if you'd like. But just make each of these 20% gray, and it'll really make the change pop that way. Great. So now you can see that the majority of the area here didn't change because it is gray. So there wasn't a difference in moisture content from 2018 to 2019. But there are some regions, in particular along the rivers, where we see a really high increase in water content. So again, you can come in and zoom to these regions and take a look. There are some regions that were actually drier in 2019 than were in 2018, but this here really allows you to quantify the difference between those two dates. So a lot of this region, these farms along the river here, have been flooded in 2019, and you could see a large increase in the amount of moisture here along these flooded agricultural regions. Same thing along much of the riverbed here in different places. So you can come in and analyze this and really take a look. I also love to sort of turn off and on layers in order to orient myself in space and time. So you could see here along the border how much of these agricultural fields are actually flooded in the 2019 time period. So this was a really large-scale event across the Great Plains and the Midwest, where flooding occurred in many different regions. So that concludes the change detection exercise for this week. We identified change through a few different methods, and then ended on this difference map, which really highlights the flooding that occurred in 2019. So thanks again to everyone for being here today. On Thursday, we will discuss time series analysis, which will be really exciting. So do please come back and join us for that. Thank you all.
Okay, great. Thanks, Amber. What I'm going to do is share my screen so you can see the questions and answers. So just bear with me for a second. I think I got it. One thing that I also realized is that this session, today's session, is actually the last session that we will be using ArcGIS. So Thursday, we're going to be using a web tool called Appears to look at some time series. And then next week is all web tools. So this is, again, this is the last week for using ArcGIS, which will be in some ways a little bit easier, because I know some of you have had issues using ArcGIS. So hopefully you can all see the question and answer document. And I'm just going to go through these questions. There's been a few of them popping up. The first one is, if the same sensor is to be used for change detection, so this was from the lecture early on, is there a way to use two different sensors, say from Landsat 5 and Landsat 8, to get a change detection reading for, say, the last 25 to 30 years? Yes, you can definitely use images from two Landsat sensors. The main thing to remember is that those images need to have surface reflectance. They need to be surface reflectance products. So they need to have had radiometric correction as well as atmospheric correction. And then you can compare those different images. The really great thing now these days is that you can get those Landsat images already corrected, atmospherically corrected. But if you do get imagery that's not corrected, then you have to run your own atmospheric correction algorithm on those images. And it's the same for any imagery that you use. If you're using drone imagery, or if you're using other kinds of imagery, if it hasn't been atmospherically corrected, then you need to do that before you do this change detection. Question 2. Are there change detection methodologies specifically designed to examine changes in surface water on the landscape? So the methodologies that we've described to you are typical change detection methodologies that you can use for any type of change. The key is, which bands do you use to assess that change? So as we showed in the exercise, which was a demonstration of looking at surface water, we use the shortwave infrared band for that, because that's more sensitive to to water in the soil or on the surface. Question 3. If I were to replicate this process, flood detection, for my study area but explore vegetation change instead, am I correct in understanding that I would have to use near infrared band instead of the shortwave infrared band? For visualizing change, you could actually use either. I would say that most of the time, if you're interested in vegetation, that the near infrared band would probably be better to use, because as we have described in the past, the near infrared band is most sensitive to chlorophyll content in plants, and therefore is really great for looking at vegetation and vegetation change. Question 4. How far down does the spectral signature measure? Will this analysis, the one using the NDWI, identify surface water below tree cover? What about saturated soil, or if the water table is a few centimeters below the soil surface? So the one thing to remember about working with optical satellite imagery, so that's Landsat imagery, etc., it really only detects what you can see from above. So it doesn't detect anything below the tree cover. It can also detect saturated soil as long as you can see that saturation at the surface. So if there, for example, you can't really easily look at the water table level or something like that, there are other sensors that will allow you to do that, but Landsat is not one of them. Question 5. If half the area inside a 30 by 30 meter pixel is dry and half is flooded, what will the whole pixel be identified as? That's a great question. I would say you're rarely going to find a pixel where it's exactly half and half, something. The pixel value will be the dominant land cover value in that pixel. So whatever is probably greater than 50%, you will. And honestly, if there's water in a pixel, so if you had if it were half dry, half water, I would think that the water signal would dominate that pixel value. So you would probably mostly get a water value in that pixel value. It's an interesting question, though. Is there a way to derive a shapefile of the changed regions? This is actually another great question, because it really gets at how do you quantify what you've done, right? So if you look at your change image that you get based on, the shortwave infrared band ratio, or any kind of band ratio, or even if you're using a single band, what you end up with is what we call a continuous image. So it's really difficult. So you have a lot of different pixel values, and it's really hard to quantify that, to quantify a continuous image. So what you do is you need to convert that to an image that has more discrete values. And there's a couple ways you can do that. One is by using raster calculator and sort of re-binning the values. So for example, you would say everything between 0 and -1, or maybe -5 to -1, is going to be called -0.5, something like that. Sorry, -0.5 to -1 is going to be called -0.5. It kind of depends on how you want to bin those values. So you basically group values within a certain range. And then once you do that, you can quantify how many pixels are within that range. It's a lot easier to do that. And then once you do that, once you have a pixel map that has fewer sort of overall values in it, then you might want to run a filter on it, kind of smooth out the extra pixel values. But then you could do a raster to vector conversion, and then you would create a shapefile from that. So there's a few more steps in place that you have to do before you can get to the point where you can quantify your change. Okay, let me see if there's any more questions here. Looks like that is it for now. So I want to wish you luck on doing the exercise. Again, if you have any questions at all, please feel free to email us. And if you can, if you have specific issues that are happening, if you could send us a screenshot or something like that, that would be really helpful for us. And if possible, we can also possibly hop on a video call with you too and kind of work through some of those issues. Other than that, we're looking forward to talking with you again on Thursday about time series analysis using Appears, which is a really cool tool. Oh my goodness. I'm mixing up my words, but anyway, it is a cool tool that you don't want to miss. So hope you all have a great day, and we will talk to you on Thursday.